And today we will cover Chapter 4, which is the normal distribution and maybe some applications of it. But before I go on, well, thank you. We already have a volunteer. Are there any questions from Chapter 3, in particular the binomial random variables? We will be revisiting binomial random variables later today, and I just want to make sure everyone feels comfortable with that. Or actually, there's a few things I want to clarify, whether or not there are questions. But did the homework feel okay for the most part? Okay. All right. Okay. So let me just cover just a quick review of binomial. And so in our problem, you will be given n and p. Okay. And you are, the problem will ask for probability of j successes. Okay. And so to answer that, the probability of having y equal to j successes is equal to n choose j, p raised to the j, 1 minus p raised to the n minus j. I hope this looks familiar to you all. Okay, so this is a simple example. I think one from the textbook was something like something like this, but not exactly like this. But maybe it said something like 60% of seashells, have stripes or something. Okay, and maybe you take 10 random shells, and then asks, what is the probability that 6 have stripes? So in this case, we have n equal to 10, p equal to 0.6, 60%, and here we're asking for j equal to 6. So we would do 10 choose 6, 0.6 raised to the 6, and 0.4 raised to the 4. I probably should have picked different numbers so we don't have so many 6s and 4s, but anyway, that's what we have. You plug that into your calculator, you get an answer. And there you go. We might change the question. Okay, the question can also be rewritten as instead of what is the probability that 6 have stripes, the exact same question could be asked, what is the probability that 60% of your sample has stripes? These two questions are the exact same question. Okay, it's just one, we've said we're looking for 6 shells with stripes, and here we've kind of twisted that around to say 60% of the sample. Our sample has 10 shells in it, So 60% of the sample is equal to 6 shells. And so this question will have the same answer as this question. Is that okay? Okay. And I think there are a few questions in the book, and historically these have thrown off our students a little bit. And it would ask something like, what's the probability that it's, what is it, within such and such, where is it? 364, yeah, instead of 60%, it might say, what's the probability that 50% of your sample has stripes? Okay, so if it says, what's the probability that 50% of your sample has stripes? Well, you look at how many shells are in your sample. Okay, your sample has 10 shells. So to have 50% of your sample to be striped, that would be 5 shells. Okay, and then so all it's doing is it's just changing. Put J for J. It's just changing J from a count into a percentage. Okay. And we might things might get a little more odd too. Okay. So let's say we still have this setup. 60% of seashells have stripes, and the question says, what is the probability that between 50% and 80% of the shells are striped? Okay. What is this essentially asking? Between 5 and 8, okay? And maybe I should put somewhere in there inclusive. Okay, so basically we're just asking what is the probability that J is equal to 5, 6, 7, or 8? Okay, because our sample has 10 shells, and we're looking between 50 and 80%, so 5, 6, 7, and 8. Okay. This would require 4 calculations to be done, right? We would have to do, and we can see it becomes tedious, because we would have to do 10 choose 5, etc., 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 plus 10 choose 6, etc., 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 plus 10 choose 7, and 10 choose 8. But if you add all of these up, we would have our answer there. Is that okay? What if I changed this and said, instead of 10 random shells, let's say I'm going to take 20 random shells. So we still have, say, 60% of seashells have stripes, but we're going to take 20 random shells. Okay. I'm still going to ask the question, what is the probability that between 50% and 80% of the shells are striped? Inclusive. So what happens now? Yeah, so my J's change to what? 10 to 10, 11, 12 to 16. Can everyone see that? Any confusion here? We're good. Okay. And then so here we would have a lot more numbers to compute. We would have 20 choose 10 plus 20 choose 11 plus 20 choose 12 all the way up to 20 choose 16. Okay, that would be 7 numbers to calculate, you know, and each of these would have 0.6 to the 16 and 0.4 to the 4, etc., etc., etc. Okay, and so we can see that would be rather tedious for us to do, but it's doable. But we'll revisit these types of questions at the end of the day. Okay. All right. And is everyone okay with using the n choose j function on their calculators or whatnot? If you had trouble with it, in the tables that I passed out, the very last page, binomial coefficients, you can look up n choose j. And so you can see if n is 10 and j is 5, you have 252, and so on and so forth. Okay. So that's available too. These numbers grow very quickly, huh? 20 choose 10, there's 184,756, okay? When you play the lotto, or actually the lotto is all complicated now. Now they have like a mega ball and the other numbers and things like that. It's like, I don't know, I don't even know how many numbers, but it's like 60 numbers and you're picking 5 or 6 of them or something. And if you try to do the math behind like 60 choose 6 or 60 choose 5 or whatever, these are astronomically large numbers, and so the probability of you getting all of those numbers is incredibly low. The joke is that the lottery is a tax for the statistically uneducated, but anyway, supposedly it goes towards education and things. I don't know. I think there's, well, maybe you pay $1 for the thrill of dreaming, but don't expect to actually win. Anyway, that's my rant on the lottery. We'll go on and we'll learn the normal distribution, chapter 4. Okay, so the normal distribution, it's technically a random variable. And it's a continuous random variable, okay? Okay. Do we remember our definition, or kind of our loose definition of what a random variable is? We said we can call something a random variable if it's the result of a random experiment, and that result is a number. Okay. So we said you could roll a die, and we look at what face the die lands on. Or we could spin that wheel and, you know, how much money you win. Is that what I said here? So on the game we said you spin the wheel and however much you win, the amount you win is a random variable. Okay. For things like the normal distribution, it could be like we select a person at random and we're going to measure this person's height. Or we select a person at random and we measure the circumference of this person's head, or, you know, whatever it might be. Okay, we are selecting someone at random, so that is our random element in this random trial. And the outcome is a number because we're not actually interested in, we might be interested in the person, but what we're recording is some measurement, some numeric measurement about this person. The height, head circumference, whatever it might be. Okay. It's a continuous random variable because you could imagine if we had very accurate measuring tools, someone's head circumference could be, this many inches with a great number of decimals if we could be very precise about it. Okay? And if we had very accurate tools, it's probably very unlikely for two people to have the exact same head circumference or head measurements. Okay? They might be very similar, but it's probably unlikely for two people to have the exact same measurement out to, say, 4 or 5 decimals. Yeah, that might happen, okay? But continuous just because pretty much any value on the spectrum is valid, okay? So the normal distribution describes a class of random variables, or not even a class, it's just some random variables will fit the normal distribution, okay? So let me just paraphrase all of that I said. Okay, so this is the outcome to a random experiment, a random trial. The outcome is a number. So, example. Pick a person at random. Measure this person's head circumference. Okay. When we graph the normal distribution, it looks like this. Okay. So we would describe the shape of this thing to be what? Unimodal and symmetric, right? This right here in the center, this is the mean, okay? And that makes sense because the mean is the balancing point. So it looks like it would be balanced right here. So, and it's also the median, okay? And it seems, that also seems clear because this seems to split our graph into half. 50% is less, 50% is greater. So this point right here is both the mean and the median, okay? We often prefer to use the mean, but for normal distributions, the mean and the median are equivalent. And because we are talking about the mean of a random variable, what symbol do we use? Mu, okay? Mean of a random variable, we use mu. Okay. If it's the mean of a sample, we use y bar, or x bar, if you use x's instead of y's. So it's the mean of a random variable, so we use mu. And the standard deviation has symbol sigma. To be unimodal and symmetric, what this means is that values near the mean are most common, okay? Because we have a peak right here, the values here around the mean are most common. And as we go further away from the mean, those values become less and less common. So as we go further out, you can see the probability drop off. And this applies in both directions, okay? And it applies equally so in both directions. So if we go larger than the mean, those values become less common. If we go smaller than the mean, those values also become less common until, you know, we are significantly below or significantly above, and we have very few values out at the extremes, okay? And we have something called the empirical rule, which serves as kind of a rule of thumb regarding the normal distribution. So this right here would be the mean, and I will draw lines right there, and right there, and I'll try to space these out evenly, but I don't know if I'm succeeding or failing. So if my picture were accurate, you know, the space between here and here, and here and here and here and here, they're all equal, okay? And this distance here, this is 1 standard deviation, okay? So the distance from here to here is 1 standard deviation, so I'm drawing a sigma right there. And actually, let me replace the word mean with mu. Okay, so this spot right here is mu plus sigma. Okay, and this is also 1 standard deviation. So this spot right here would be mu plus what? Mu plus 2 sigma. And right here I would have mu plus 3 sigma. And just the opposite over here. Mu minus 1 sigma, mu minus 2 sigma, mu minus 3 sigma. All of these are 1 standard deviation, 1 sigma. Is that okay? Any confusion, any questions? Can everyone read my writing? I hope. All right, so the empirical rule so empirical means based on data. Or what's observable, I guess. Empiricism, all that. Actually, so let me write this over here. It says if data is unimodal and symmetric, then, okay, so about approximately 68%, okay, or we can also just say about 2/3 of the data will be within one standard deviation of the mean, or in other words, is between mu minus sigma and mu plus a sigma. About 95% of the data is within 2 sigma of the mean, and almost all, not quite, is within 3 standard deviations of the mean. So I'm writing these shorthand with the symbols instead. I hope that's okay. Okay, so just example. So we can say in the US, the heights of males, of adult males, approximately normal, with mu equal to 70 inches, so that's 5'10", and standard deviation equal to 3 inches. Okay, these are not the most accurate figures. It's probably closer to 69.5 inches and maybe more like 2.8 or 2.9 inches for the standard deviation, but for simplicity we're just going to use these nice round numbers. So according to our empirical rule, I would, or just our model, we would put 70 in the middle, and so within one standard deviation would be going out to 73 and 67, okay? And so the empirical rule says about 2/3, or about 68% of US males from US adult males are between 5'7", 67 inches, and 6'1", 73 inches. And that seems to match our intuitive sense of heights. If we go down 2 standard deviations, we're down to 64 inches and 77 inches. Okay. Did I? Oh, 76 inches. Can't add. All right. And so we would say about 95% are between 5'4" and 6'4". All right. So that means about 1 in 20 are outside of that range. Also seems to match our intuitive sense. Although maybe because of athletics being televised, we have maybe slightly skewed perception of the tall side of the spectrum. Okay, don't have very many televised events that highlight people on the lower side of the spectrum, but you know, pretty much many sports on TV that have an audience generally favors the taller people. Okay. And then if we go out, you know, we would be down to 5'1", 61 inches, and 79 inches. So 5'1" and 6'7", and that says almost all adult males are between 5'1" and 6'7", with, you know, maybe about 3 in 1,000. This is what it says, 99.7%. So almost all, but not everyone, about 3 in 1,000 are outside of that range. Okay. And also that seems to match most of our intuitive sense. Okay. And of course, height curves, the distribution of heights of U.S. males in the United States, U.S. males, obviously, in the United States, of U.S. males is not going to be perfectly normal, okay? It's not going to follow the normal distribution exactly, so these proportions will not be exactly accurate, but it fits it pretty well, and so this forms a good rule of thumb. Okay. All right, let's see if, what if I say approximately what percentage of males are shorter than 5'7"? So don't shout out your answer. Think of it in your head. So based on what we understand about the empirical rule, try to come up with a number for approximately what percentage of U.S. adult males are shorter than 67 inches or 5'7"? Okay, yeah. So just we'll give a moment for the rest of the class to figure this out. Okay, do we kind of have a number in mind? What do we think? About 16%. 16%. Okay, are we in agreement there? All right, because we can see that 68%. So about 68% is here. So that means between this wedge over here and this wedge over here, I would have 32%. Okay, and because it's symmetric, we can assume that this side and this side and this side are the same. So 32% divided by 2 would put 16% over here and 16% over here. Okay. All right. So if I said, okay. So again, just think about this in your head. Don't shout out your answer. This one's probably a little easier to come up with. But so if I say about approximately what percentage of males are taller than 76 inches, approximately what percentage are taller than 6'4", don't shout out your answer, but come up with an approximate percentage. Okay, and we would say approximately what? About 2.5%, right? Because we said 95% is between here and here, so that leaves a total of 5% in this wedge and this wedge combined. So if we're only looking at one of these wedges, we would have about 2.5%. Okay. Good. Have I lost anyone? Okay. Good. Don't be shy or embarrassed to ask questions. Okay. Some of us are not as good at processing visual information as well as others.
I have a question.
Yes.
I'm still struggling with how you know when something is a random variable is because examples like height, which is, I don't really understand the difference between when you actually measure the height and you get the answer versus this is a random variable.
Well, if we just take our classroom and I measure everybody's heights, I have data, okay? And that would be that, okay? If I frame it a slightly different way, okay? And I say I'm going to pick a student at random. So I have, I have all of your names on the roster, okay? And I could label them. I could put them all on slips of paper, put them into a hat, shake up the hat, and draw one of your names out, okay? So that would be a random selection. And I could ask for the student that I selected. I could ask for the student's height. Okay. So the result, the measurement that I'm getting here is the result of a random process. Okay. And so that makes it a random variable.
How is that different from doing random sampling at the same
Oh, no. Okay, so so that is random sampling. Okay. So when you do random sampling, the resulting data could be thought of as the result of a random process. That's also fair. Okay, yeah, if you successfully pull off random sampling. Let me think. So sometimes we, when we look at, I don't know, numbers and such, we will treat them as the result of a random process. Analyze it as a random variable and treat them as such. Other times, we just want to look at sample statistics and say this is data that we have. What's the standard deviation? What's the mean? And we're not so interested in the fact that it came from random sampling or not. Okay. So anyway, right now we're just learning about the process of the properties of the normal distribution, okay. And it will come very useful in the future, in next week, okay. But we first have to establish our foundation here. Okay, so don't worry too much about the nuances of what it means to be a random variable. Okay, so good. You were able to answer questions like, what percentage are shorter than 67, and what percentage is taller than 76. What if I ask for a number that's not there? What if I say, about what percentage is shorter than 66 inches? How would you answer this? Okay. Well, that question cannot be answered so easily using the empirical rule. Okay. We know that the percentage shorter than 66 inches would be less than 16%, right? And also more than 2.5%. But beyond that, it's hard to kind of come up with a good answer. Okay? And so to aid us with that, we have the normal table. Okay? And so for the normal table, to use the normal table, we're going to learn about z-scores, or we have to use z-scores to answer a question. Okay? So a z-score is the number of standard deviations we are from the mean. So over here I said the mean of heights for US males is 70 inches and the standard deviation is 3. So 67 inches is equivalent to z equal -1. Okay. Because 67 inches is 3 inches below the mean, and that is equal to being 1 standard deviation below the mean. So 67 inches is equal to z equal to -1.
So -1 is really the
Not the standard deviation of 3. It's -1 is saying we are 1 standard deviation below the mean. 67 inches is 1 standard deviation below the mean. That's what it's saying. Each standard deviation is 3 inches. Is that okay? Here, let's try something out. Don't shout this out, but 66 inches would then have a z-score of, don't shout it out, but think of your answer. Okay, now go ahead and say it. -1.333. Okay? So what we are doing here is we are saying, well, 66 inches, that's 4 inches below the mean. Okay? 66 is 4 inches below the mean. But we're not interested in just how far we are from the mean. We want to know how many standard deviations we are from the mean. Okay? Each standard deviation is 3 inches. So I can just take this distance and divide by 3. Okay, and so I would be 4/3 of a standard deviation below the mean. Oops. So that's -1.333. Okay. It might feel weird, but you guys do this all the time. Okay. If you grew up in the United States, you know that 12 inches is equal to 1 foot. All right. So somebody could tell you that, you know, the height of some door is 84 inches, and in your head you say, oh, that's equal to 7 feet. Okay? You're just taking a distance and dividing that distance by 12. And that's all we're doing here. We're just taking a distance, which is how far a certain point is from the mean, and we're dividing that by how large our standard deviation is. Okay? So we don't want to know, how many feet we are from the mean or how many inches we are from the mean. We want to know how many standard deviations we are from the mean. Are there any questions? Okay, so the formula for the z-score is equal to whatever point you are looking at, the y, and you subtract off the mean, and you take that distance, and you're going to divide by the standard deviation, sigma. Is that okay? So let's just try a few things. All right. So find the z-score of a man who is ... Okay, so we'll say 76 inches tall, and we will say 70 inches tall. 65 inches tall. Okay, so go ahead and find these z-scores. Again, keeping in mind that for the heights of men, the mean is 70 and the standard deviation is 3. Alright, so what do we have? We have positive 2. Okay? So you just do 76 minus 70, gives you 6. You divide that by 3, and we get 2. What about here? 0. Okay? the mean is 70. So if a man is 70 inches tall, how far is he from the mean? He's 0. He's right at the mean. So his Z-score is 0. And this one would be negative 1.667, or whatever you round off to. 65 minus 70 gives you negative 5. You divide that by 3. 1.667. All right, give me a thumbs up if you're with me. Okay. All right. I think most of you gave me a thumbs up. Okay, just because you guys are very quiet, so sometimes it's hard to gauge. Maybe I'm boring you to tears. I don't know. So always a smile and a head nod. That's always good too. And now you're with me. Yes.
So Z-scores for normal curve.